p15. We're getting into the second fundamental theorem of calculus, which is also known as the Evaluation Theorem, which is also known as Fundamental Theorem of Calculus Part 2. All right, so you can see that we got a lot of craziness going on with this equation. So it's essentially talking about finding the derivative of an antiderivative. All right, so the idea behind it is using the fundamental theorem of calculus part 2, or evaluation theorem. It allows us to orchestrate a change in variables. All right, now there's a variety of different reasons why one would want to change variables in an equation, but I'll just keep it simple right now and say that we want to change variables. Why? Because we might be instructed to. All right. Now, the extension on that, has implications in calculus 3. So when you get there, you'll see a lot more of what I'm talking about. But let's say, for example, I wanted to do a coordinate system change. Right, so instead of working with rectangular coordinates, I wanted to work with polar coordinates. Right, fundamental theorem of calculus could come into play there. All right, if I wanted to do just a simple unit change, inches to centimeters, we could redefine our x values, quote unquote x values, to instead of being measured in inches, they would be measured in centimeters. So we could apply the second fundamental theorem of calculus there. A lot of this won't really have too much meaning until we actually start diving into the process. So let's, without further ado, get into that. All right. So first thing we're going to do is pop in a function. So y equals the cosine of x, or f of x equals the cosine of x. Make sure you're in the right mode, which would be radian mode. All right. Now, it says in the example, consider the values for the function f of x equals the antiderivative of cosine t dt. All right. So it's in terms of t. Now we're integrating that over the interval of 0 to x, and we're looking at this specifically on the interval of 0 to pi over 2. All right, so we know what a cosine function looks like, but just in case you don't, zoom trig is a good option to get you started. Gives you a quick look. All right. Now, most of us know what a sine and cosine function look like, but maybe it's the funkier trig functions that you need help with. Zoom trig is a good place to start for stuff like that too. All right. So when you see something like capital F of 0, so f of x is, and I'm just going to rewrite it over here just so I don't have to scroll back and forth, but capital F of x is defined as the integral over the interval of 0 to x of f of t dt, all right, where f of t is given as cosine of t. All right, so we're looking at f of x is equal to the integral over the interval of a to b, 0 to x of cosine of t dt. So what they're asking us to do here in the first problem, or first part of the problem, is to evaluate this for when x is equal to 0. All right, so that's the same as saying, and didn't really give myself enough room, so I'm going to shrink this down a schmidgy. And rewrite it as 0 to 0, because the x value is now 0, of cosine of t dt. All right. We're not going anywhere, so we're not accumulating any area. So this would result in a value of 0. All right, so we're going to keep track of that. All right, so just kind of make a mental note or make a table of values. All right, so either way. All right, so that's what I'm going to do, is I'm going to make a table of values. So x and the f of x. So 0 gives a 0. All right. So next up is pi over 6. So integral over the interval of 0 to pi over 6 of cosine t dt. Antiderivative of cosine of t with respect to t is sine of t over the interval of 0 to pi over 6. That's going to give us a result of, well, sine of pi over 6 minus sine of 0. First fundamental theorem of calculus at work here. All right. So you pop in your upper bound, you pop in your lower bound, and you subtract. All right, sine of pi over 6, unit circle, 1/2. Sine of 0, 0, result is going to be equal to 1/2. So pi over 6 gets you a 1/2. Okay. Pi over 4. All right, so a lot of the same stuff happening again. So what I'm going to do is kind of get a little slick here. Pi over 4. We know the sine of 0 is going to give us a 0, so ultimately we don't really need to account for that anymore, because every single time we evaluate our definite integral, we're going to end up with a minus 0, so we could just ignore that. So really, essentially, we're taking the antiderivative and plugging in the upper bound. Doesn't always play out that way, but when it does, it's kind of nice. All right, so we're looking for the sine of pi over 4. Again, unit circle, radical 2 over 2. So pi over 4 gives you a radical 2 over 2. Okay. So continuing on, same deal, same antiderivative. Now we're plugging in a pi over 3. Those teachers weren't lying. It is important that you know your unit circle. Alright, so if you haven't made it a priority to study the unit circle, add it to the list of things to do. Alright, especially before Calc 3, if that's a course you're going to be taking, I can promise you that the unit circle is going to be a big deal, a very, very big deal. Right? As in, you probably will not meet with much success in the course unless you know the unit circle. Right. So pi over 3 gives you radical 3 over 2. Even for folks like me, who, when I teach Calc 3, I'm very forgiving when it comes to the use of technology. I use the calculator a lot. All right, I use this calculator, I use Desmos, I use GeoGebra, like a lot. And the unit circle still ends up being the kind of thing that you need to make a priority. Right, so do it. Anyway, pi over 2 is next on the list. So sine of pi over 2 is equal to 1. So pi over 2 gives you a 1. So this table of values here can actually be plotted. So that's what I'm going to do. You don't really need to plot it, because if you notice a relationship or a trend, you might be able to kind of pull that out and draw a conclusion from there. But I'm just going to kind of do it to drive the point home. So we're going from 0 to pi over 2. So I'll call this pi over 2 here, for example. Let me clean that up a little bit. All right. So break it up into thirds. Pi over 6, pi over 3. That's 30, 60, 90. And then smack dab in the middle of pi over 6 and pi over 3 is the pi over 4. All right. All right. Now, we're going from 0 to 1 on the y-axis. So I can plot that, but then I'm also going to have some decimal values along the way. 0.5 is the obvious one. Radical 2 over 2 is about 0.7-ish. So what I'll do is I'll break this up. 1, 6. So I'll put 4 little tick marks in here. 3, 4. So 0.6, 0.7, 0.8, 0.9, and then 1. Right? Because rad 2 over 2 is about 0.7. Rad 3 over 2 is about 0.87. So a little short of 0.9. So we could ballpark it that way. All right. So 0, a half, around 0.7, around 0.9, and around a 1. Well, definitely a 1. All right, so we're looking at something along these lines. Now, if I continue the process, I only went out to pi over 2. What if I went to 2 pi over 3, and then 3 pi over 4, and so on? The trend would continue. It's just a question of what the trend is. Well, we started off with the antiderivative of a cosine function, and we ended up with a sine function as a result. So what we arrive at here is the idea that what you're doing when you're finding antiderivatives, you're collecting areas, you're accumulating areas, but those areas correspond to the coordinates of another function. All right. So what the x values here are, these x values, x comma y in terms of coordinate axes, but the x values, the quote-unquote x values, they could mean a bunch of different things. All right. So we're plugging in an unknown x in for the t bounds. All right. So these are actually t values in our original function. All right. So we had t against some value that we were calling f, capital F. All right, and that was given us sorry, I put that in the wrong place. I don't even know why I shifted over there. So against f. All right, so our t values against the f. All right, but as it turns out, those t values correspond with x values. So the t's are actually being transformed into x values, and yet we're still ending up with an area, an accumulation of area. So we're getting x against some capital F. All right, so if we wanted to, what we could do is then differentiate this function, which is now pretty clearly y equals the sine of x. We could differentiate that and get cosine of x, which is what originally was defined as f of x. All right, so it allows us to take a function that was not defined in terms of x and write it in such a way that it is defined in terms of x, and vice versa. All right, so that's one of the more meaningful things or aspects of the fundamental theorem of calculus part 2, or consequences of it, if you will. But you kind of run into the issue in this course anyway of, all right, cool, that's all so very wonderful and intriguing. Tell me more. Like, what are we going to use this for? And I have to be the one to say, well, we'll get there in Calc 3, and it's like, oh, okay, that's sad, but that's unfortunately the truth.